happened here? Okay, so the exam went really well, and I'll post your scores on Friday, if not, maybe even earlier if I get them back sooner. But I'll post them, and then I'll bring your exams to class next time. So we're skipping chapters 19 and 20. So those were, we did type 18, which was on power, type 1 and type 2 errors, and we're in the notebook, 19 and 20 continue with that. So if you want to learn more about that or just want extra bonus points, I'll post the pre-lectures, and they'll be due Sunday. And another R bonus is coming up, and that will be due next week, next Friday. So this Friday, we just have the, don't forget to do those pre-lectures for today's lecture, which is going to be on correlation and regression. And the calendar is updated for the rest of the semester. So if you want to look at that, go ahead. It's I don't have all the bonus up, but I have everything else up. So let's just go to any questions on anything about the exam, or so let's start our new section on correlation and regression. So let's go to the document camera now. And we're on page 102 here. That looks pretty light. Can you guys see that pretty clearly? Does that look normal to you guys? Not if it looks okay. It's okay. All right, so previously what we've been doing when we did statistics, we looked at statistics at variables separately. Like we looked at height and weight, etc. separately. So we computed the descriptive statistics like the average and the median and the standard deviation, and did a graphical display with the histogram. Well, now we're going to look at bivariate data, two variables at the same time in their relationship. So the statistic we're going to be looking at is the correlation coefficient, which is a measure of the linear relationship between two quantitative variables. It measures how tightly those points are clustered around a line. And the graphical display that we're going to be using instead of a histogram, because we want to show both x and y together, is a scatter plot, where we'll have x on the variable that is called the independent variable. The convention is called the x variable, the independent variable, and the y variable, the dependent, because we're thinking of x predicting y. Like if you were thinking about how many hours you study, predicting your score in the exam, you'd think x would be how many hours you study, because it would influence the exam score. But the correlation coefficient doesn't depend on which you choose as x or y. And sometimes the variables, you can't think of them that way, but you could still do a scatter plot, and you can still do a correlation coefficient as long as the points hug a line. Now, for example, let's look at these here. So these points have a very clear relationship here. But the question is it appropriate to use R to describe the relationship here? Remember, this one is clearly appropriate because the points are hugging a line, and this gives you you can see very clearly as x goes up, so does y. This looks like almost a perfect correlation. You could write an equation describing this and perfectly predict y from x, right? So this is yes, it would be a great statistic. And here, if you have a perfect relationship, R is equal to 1 or negative 1. 1 because if you have a positive relationship, as x increases, y increases, and negative 1 would be the opposite. But, so, yeah, it's almost 1. But now look at this. You still can almost perfectly predict x from y. You can still, but you'd have to describe it with a curve, a quadratic equation. And that, what would the correlation compute? Well, it hugs a line this way, and it hugs a line that way. And R, you know what R would give you? It would erroneously give you an R equals 0. And you don't want that, because that's completely different. So no, it's not the appropriate statistic to use here. Why? Because R measures linear relationships, and this right here is a curve. And it would give you, how about this one? Here's another one where there's clearly no relationship. Here, there's clearly no relationship. As x goes up, it tells you nothing about y. If I tell you you're down here or down here, you have no more clue about what y is. And so it seems like r equal to 0, meaning there's no correlation between x and y, is the appropriate statistic. So here, r equals 0 is appropriate. Here, if you computed a correlation coefficient, it would give you 0, but it's really not appropriate because you'd think, oh, there's no relation between x and y when there's almost a perfect one. It's just not a linear one. Okay, so this one is a very nice, typical, nice correlation here between, this is yes, of course you can use r here. This is there's a very nice but not perfect, very strong but not perfect relation between x and y. These are all between x and y here. And so this is great. Now this one, what do you think about this one? This one sort of has two separate groups. So what would happen is, within each group, there's a very nice negative relationship, right? So you think, oh, that's fine. And what we should do in this case, there's two separate groups. Let's think about it. So is it yes or no? What we have here is two very distinct groups. So what should we do with this? And if you see something like this is a way that people often could lie with statistics, or it could just be really crazy, because what would happen is that R would give you a positive relationship. It would look at, okay, we have a group down here and a group up here, and it would say they're positively correlated, that as x goes up, y goes up. But that's completely crazy, because within either group, there's clearly a negative relationship. So you have to be careful about that, and the answer is no, because there's two distinct groups. And what you'd need to do is, of course, split it into two separate plots. Okay? Any questions on that? All right. Now, so it does not measure clustering around a curve. All right, so now, as I said, the correlation coefficient is always between, a perfect positive correlation is 1, and a perfect negative correlation is -1. And if you have nothing, it's 0. So it's always between -1 and 1. And the closer the points hug a line with a positive slope, the closer r is to 1, and the closer they hug a line with a negative slope, the closer it is to -1. All right, now, so I said a correlation of 1 or -1 means you can perfectly predict one from the other. That's true, but just because you can perfectly predict one set of points from another does not mean the correlation coefficient is 1, because unless it's a line, because you could have this situation. All right, so this means when r is -1 or 1, all points lie on a line. So you could describe the relationship with the formula, y equals mx plus b. All right. So that's what I wanted to put right there. Sorry, I wrote it in the wrong line. And a correlation of 0 means knowing one variable gives you no information about the other. Okay. So now, let's turn the page here. And now, match the correlation coefficients here. These correlation coefficients, boy, they're hard to see. Let's zoom in a little bit. Can you see them better now? Okay, so here you have these four correlation coefficients. This is -1, this is a -1, this is positive, and this is positive. And we're supposed to look at these plots right here and match them. Well, first let's look at these plots. This is clearly a positive one, right? And this is clearly a -1. This one looks what? This one looks slightly negative, doesn't it? Can you see that slightly negative? If you had, see, these are, okay, so why don't we do the two easy ones first? This is a strong positive correlation, so which is our strongest? That's going to be this one, positive 0.88. Okay, so that's going to be B. And this is a very strong negative. Strong means absolute value close to 1. So that's a strong negative one. So that's going to be this one. So now we know these two. Now you see that we have kind of weak correlations here. We have a little bit stronger negative correlation. I bet that's, see, this is a weak negative correlation. So that's going to be A. And then we're left with D. And I can't even really, can you tell there's a slight positive? A very slight positive correlation with that one. So it would look like this. All right? That's the idea. Now, the reason why you can actually distinguish pretty easily, except for maybe these two, is because these plots were all drawn with the same scale. Okay? They were all these have the same, this is what I'm saying, the average and standard deviations of X and Y are the same in each of the 4 plots. So in other words, here, what you have is, okay, so but these do not tell you the relationship between the two of them. They give you no information. Remember, the average and standard deviations don't tell you anything about the relationship between X and Y. So if they have the same, that means they're basically drawn in the same box. They have the same spread and the same center. That's all you know. But they could look wildly different, and that's because they have different R's. Okay? And the reason they're easy to distinguish, because they're all drawn with the same averages and standard deviations. Often you'll see plots with different averages and standard deviations, and it's difficult sometimes to tell which ones actually have stronger R's or weaker R's, because R is in relation to the standard deviations. But here you can match them up. Let's try an iClicker and see if you can, we'll do a game. There's a game you might want to play just to practice on our data program. So let's go over here and pull that up. Okay, so it's called guessing correlations right here. And we'll do the easy ones together, and then I'll do the harder ones as an iClicker. So this is pretty easy. You see that it's a very strong correlation, and among these choices, it's going to be this one. And look at this. This has a very strong correlation too. It's the exact opposite, negative, right? Oh, these aren't too hard, but which one do you think? Okay, take this one. So the two left, which one do you think this one is? Choose A if you think it's I'll start it. Okay, so if you think this one is 0.38, choose A. If you think it's 0.12, choose B. We're doing this one. So just vote, and then we'll check it out. So just vote A or B. Okay, I'm going to stop it now and see what you said. I hope you chose A. Yes, most of you did. That looks like a stronger positive correlation than this one. Doesn't that look stronger? Can't you sort of, this one doesn't, do you see the trend, the linear trend there? That one's a stronger positive correlation. So now let's just make sure we were right. We said this one was 0.38, and we said this one was 0.12, and let's check our answers. Yes, yay. Okay, so you can do this yourself. You just go to, right here to the data, click on the data program, and click on guessing correlations. All right, so let's go back to the document camera and move on. Okay, so now the question is, correlation coefficient measures the strength of association between X and Y. It measures how closely they hug a line, the line of perfect correlations. That's what it is. So which line is that? That's called the SD line. And I bet most of you, unless you took Stat 100, are not familiar with this line. You're familiar with a different line called the regression line, which is the best predictor line, the line that we use to make predictions for y given x. But first, let's look at this regression line, this standard deviation line. And this is the line when there's a perfect correlation. So this is line when r is equal to either positive or negative 1. It's called the standard deviation line. And it always goes through the point of averages, and this is the slope of the line. All right, so you'll understand it better if we actually draw it. So it always goes through here's a data set, and here we have the average exams. What is this? Exams, this is x on this axis, x, and on this is finals. So exams predicting finals. And you can see there's a positive trend here. There should be. So here is, let's look at this. So here's our point of averages. 83 was the average for the exams and 74. So let's look at that. So that's about 80, 70 is about right there. So we have 83 and 74. I'll guess it's about there. Okay? So that is 8374. All right, what is it in terms of z-scores? What do you think that is? If it's exactly at the average, both of them, they're both what? This is zx and this is zy. They're both z of 0, right? Isn't the average? So that's what it is. And it's a z equal to 0, 0. That's our point of averages right there. Now, that's always on think of the SD line as the line of perfect correlation. So if you're one standard deviation, if your z-score above average in one, z is equal to 1, then it'll be z equals 1 in the other, all right? So, so to draw it, what would we do? We'd go one standard deviation over in the x direction and go up one standard deviation in the y direction. Why are we doing this? Think of it this way. We're trying to get this correlation between x and y, but they might not, in this case, they're in the same units, but it's easier to picture. Imagine we're doing height and weight. What would it mean to have a perfect correlation? It doesn't mean that they have the same numbers. It means that they have the same z-scores. Same with exams and finals here. They have different averages and different standard deviations. So if you're trying, you have to have a common measuring stick to be able to relate x and y. We need to get a common measuring stick. So we remove the units and express with the correlation coefficient is computed in standard units between x and y. So think of it as z-scores here. So this is a z-score of 0, 0. Now this, when there's a perfect correlation, what that means is that zy is equal to zx. Those two are equal. That's what a perfect correlation means. It doesn't mean your exam score and your final score are the same. It means however much above average you are on one, you're exactly that much above average relative to everybody else on the other. Does that make sense to everybody? Okay, so how are we going to get the standard deviation line? Well, we just need 2 points to determine a line, right? So why don't we just go over one standard deviation in the x direction. If we went over 1, that would be going over 9, right? So we go over 1. That would take us to 92, right? So that would take us to, this must be 90 here. That's the page number. So it would take us over to about 92. That would be one standard deviation in this direction. Okay? I'll put that down here. 1 SD of x. So that would go over 1. And then for a perfect correlation, now we're at 92. For a perfect correlation, how far are we going to go up? Well, one standard deviation in the y direction. And that's right here. So we'll go up 10 to 84. So 84 looks like it's about there. Okay. So that's one standard deviation in the y direction. And that takes us up to 92 was 9 in this direction, and then we're going to go from 74 up 10 to 84. Okay? And these 2 points determine a line. Any 2 points, but this is the SD line. And by the way, this is, what would this be? This is right here, is z equals 1, 1. This is equals 0. See? So the SD line is the line, SD line is the zy equals zx line. When you have a perfect correlation, what it means is that your x and y points match up completely in standard units. That's the way you should think about it. We have to. It's R is unit free. Yes.
So the SD line, it says that R equals 0.6, so that means that how close it is to the.
Oh yeah. Yeah. This R is not the same. Okay, so yes. So what would that mean? That's, well, that's a good question. Let's think about it. All right, she says, so what does this R.6 mean? Well, the slope of the SD line is what? It's 1 in standard units. Slope of SD line. In this case, it's positive, so it's S. Oh, so sorry. That was my bad. It's my hand doing something. There we go again. All right, so the slope of the SD line is right here, 1 standard deviation in the y direction over 1 standard deviation in the x direction. Now, what this 0.6 says in relation, it tells we have a lot of scatter here. I don't know if you can see it, but there's a lot of points around here. We don't have a perfect correlation between exams and finals. Of course not. There's a lot of scatter here. And this R equals 0.6 is actually the slope. This tells you how close these points hug a line in relation to this. So this R equals 0.6 would mean what? It would mean that instead of, so the slope, this is the regression, it's the slope of the regression line. So I'll write that first. Getting a little ahead of ourselves, but this is a good question. Slope of the regression line, and that is equal to R times SDY over SDX. Now remember, R is a fraction, so it's going to be less steep. And this tells you, instead of going over 1 standard deviation and up a whole one, we're only going to go up 0.6 of 1. So I'm going to draw it over here so you can see it better. What it means is however many standard deviations you go over in the x direction, you're not going to go up exactly those many standard deviations in the y direction. This is a correlation of 0, R equals 0, and this right here is a correlation of 1. And we're only going to go 60% of the way up, 0.6. So if you mark this off, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, etc., this would be 0.6. 1, 2, 3, 4, 5, 6. This would be R equals 0.6. And your regression line would be between those 2 points. So I'll just draw it in now. Since we're thinking of it, this would be your regression line. Your standard deviation line is a perfect correlation. And your regression line would look, I'll just draw it in like that with dotted lines. This would be the regression line, or maybe a different color. Why don't I draw it in with a different color? So this would be the regression line. And that corresponds to the 0.6. Okay? So that tells you how closely the points hug the SD line. Great question, thank you. And never mind if you get ahead with a question, it's good to connect the dots, connect when we're talking about it. All right, so that's the SD line, and this is the regression line, and it's always flatter by a factor of whatever. If it was r equals 0, it would be completely flat. Knowing 1, x would not help you predict y at all. All right, so now let's move to the next thing. So how do we compute this correlation coefficient? What do we do? Well, I just said that the correlation coefficient is measured in standard units. So you have to convert whatever values you are in to z-scores. So let's do that. So here's an example of there's 4 people here, and this is their score on quiz 1 and quiz 2. And we can graph it here, quiz 1 and quiz 2. This will be quiz 1. I'll put that on the x-axis y, because you think quiz 1 came first, it might predict quiz 2. So that would be the convention. All right, and now what do we have here? We have the point 10, 10, and then we have the point, the next one is, I'm just doing these points, 9, 7. Oh, it sounds like it's thundering out. 9, 7, 5, 9. And the last one is 4, 6. So just looking at these points, can you think there's going to be can you see that there's going to be a positive trend? It's going to have a positive correlation because you can see there's a positive trend here. All right, so now how are we going to get that correlation? So we're going to take the x's and y's and change them to z-scores. So here's zx and zy. I just said x in standard units, y in standard units, same thing. So remember how we do this? Z equals just, you should know it by now. All right, so that's all we're doing. Z equals value minus average over the standard deviation. So, we got to get these averages and standard deviations. All right, I'm just going to, okay, so the average of x here is equal to 7, and it has a different average here. Average of y is equal to 8, and the standard deviations are different too. This one is 2.5, and this one is 1.6. That's what you need. All right, now we can do it. So for the first one, we'll say, okay, 10 minus 7, right here. Our z-score is 10 minus 7. It's 3 points above, but you have to, and how many divided by its standard deviation, and this is 1.2. All right? And how about this one? Now it's the same score. Will it be the same z-score? No, because the averages and standard deviations are different. So instead, this one's 2 points above, but this, and the standard deviation is 1.6. So this is 1.25. So they're somewhat different, even though they're the same score. And you can go through all of them that way. This is 0.8. This is negative 0.8. And this one is negative 1.2, because this is 3 points below average, and this one was 3 points above. So let's do the same thing here. And when I did it, I got negative 0.625. This is below average, so it's negative. This next one is the same above, 1 point above, so it's positive. And the last one is negative. Now, they're not always symmetrical like that, but they do always sum to 0. So this column sums to 0, and so does that one. So they have to sum to 0. Because the deviations have to sum to 0. So these have to sum to 0 as well. All right, and now, what are we doing here? So we're saying zx, they're taking the products, times zy. All right? But before we do that, let's just think what we just did here, okay? So you can, why this makes sense. So let's just divide this into 4 quadrants, okay? So the average of the x's is 7. That's the average of the x's. And the average of the y's is 8. So let's just do this. So that's your average y right there. So I just wanted to show you that, okay, when both its x and y values is up here, they're both positive, right? Both above average. And when they're down here, they're both below average. So this person's quiz score was below average in both. This person's quiz scores were above average in both. Whereas these had the opposite. This one did better on quiz 1 and below average on quiz 2 and vice versa here. So when the idea of taking the products is a positive times a positive is a positive. A negative times a negative is a positive. So when you have a positive correlation, it means that negative below average values of x are associated with below average values of y, and above average values of x are associated with above average values of y. Whereas when you have a negative correlation, it's like you have the opposite. People who do below average on one do above average on the other. So now we have 1 in each quadrant, right? So you'd think maybe they all cancel out, but these are stronger. See how that's why we see the positive correlation. These are going to dominate. Imagine if they were way out here. And imagine if these negative ones were way out here, then they'd dominate. So even though we have 1 point in each quadrant, we don't get a zero correlation. So what we do when we take these products is, you'll see right away that these ones this is going to be a positive because they're both above average, right? And the negative is here. They're both, where's the negative correlation? This will be a positive 2. This is the one that's both below average, right? They're both below average. So that's going to be a negative times a negative is a positive. And these two that are opposite are going to give negative products. All right, so let's do that. So we take the product 1.2 times 1.25. And we get 1.5 here, and I got 1.5 here. And now positive times a negative, we get negative 0.5 and negative 0.5. So when we add all these up, this is what we're doing here. Let's add them up. So we're taking the sum of those products, the sum of these 4 products. So we have 1.5 plus negative 0.5 plus negative 0.5 plus 1.5, and that's 2. And then we take their average. So that gives us 0.5 positive. That's what R is. If you get a number over 1 or bigger in absolute value than 1, you've done something wrong. So these both had products of 1.5 and these both had products of 0.5, and that's why we got the positive correlation. Any questions on that? So that's how you compute a correlation coefficient. There's another computational formula. You can change this to a different computational formula, but this is by far the most intuitive one. And inside the formula, it explains what it's doing, which is why I like it. Okay. So now we are going to look at some scatter plots. And first, let's remember how we looked at how the average and standard deviation are affected when you multiply all the points by the same number or add the same value to all the points, etc. Well, it's going to be similar with the correlation coefficient. It's calculated from standard units, so it's not going to be affected by a change in scale. All right? It's not going to be. Because when so in other words, adding a constant does not, to all the x and y values, doesn't change r. Multiplying them all won't change r by the same constant. But what does multiplying by a negative constant do? What if we multiplied all the y's by a negative? That would change the sign of the correlation coefficient. But it wouldn't change the strength of it. It would just change the sign. It's either a reflection around the y-axis or the x-axis, and it would just change the sign. All right, interchanging all the x and y values is also not going to change r. So let's think of an example for all these. The correlation between height and weight. Isn't that going to be the same as the correlation between weight and height? Changing x and y is not going to change the relationship between the two of them, right? Because remember, it's just the products. All right, and changing units does not change r. That means any kind of linear transformation, adding a value or subtracting and then dividing by something is not going to change r. Because think a good way to remember this is that, let's say the correlation between height in inches and weight in pounds is not going to change if you use the metric system. It's not going to change. It's going to be the same relationship. So you'll have the same r, no matter what units you're using. And that's because the whole point of it was we changed to standard units to get a standard measuring stick. So of course, if you change back to the particular units, you're going to keep that same r. All right, now you have to be careful of these outliers. They can have a strong effect on the correlation coefficient. So what do we do with them? Like here, right here, do you see how there's a positive trend like this, but here's an outlier. And here, it looks like there's no correlation, and here's an outlier. So what do you think outliers do? For which plot below does the outlier raise the correlation coefficient? And for which does it lower it? Okay, why don't we just, let's get back to this. Let's look at some data here. Let's draw these scatter plots, okay? So let's go over to the, we could do a clicker on looking at some data. All right, so let's see. So we can, let's see, what should we do here? A scatter plot. Let's do a blank plot. And I'll draw that one. And you'll see, what do you think is going to happen? Okay, so look down here. Can you see? I have 1 point. Of course, I'm not going to get an R. But if I do 2 points, now I have a perfect correlation, right? A perfect correlation. Here is your regression line. It's perfect. You just have 2 points. All right, so now just draw what you see. All right, now let's say we have, so R is very strong, right? Now, what's going to happen if I add this outlier? If I add a point here, this is going to be your clicker question. Do you think this is going to go up or down? So I will start this. I'm going to add a point right here. So up is, if you think this will make the correlation go up, vote A. Down, vote B. And it won't change it is C. So I'll write it up on the board so you can see. And just vote. So vote A if you think R is going to go up, B if you think it's going to go down, and C if you think it's going to stay the same. And then we'll see if you're right. And you can get to this yourself. You can play around with it. All right, let's stop it and see how you voted. I hope you said it's going to go up. No, I hope you said it's going to go down, right? I hope you said that, right? Yay, you did. So let's check it. And let's put a point in and watch it. It's going to go down. Went way down. It can strongly affect correlations, okay? Strongly affected. Let's do the other example now. So we'll get a new blank plot. Okay. And let's do the other one. What did we have? Okay, so we have we have to get about like 0 correlation here. That looks about 0. I can't get exactly 0. It's hard to get exactly 0. Okay, it's very close to 0. Now what's going to happen, why don't we start this again? Okay, if I put this point up here, is that going to raise, lower, do the same thing, A, B, or C? A is going up, B is going down, and C is staying the same. Oh, shoot. Okay, so now we can check it out and see. So I'll stop it and see what you said. Great. Okay, we'll do it. So we'll put a point in here, and you're watching this. It's going to go up. It goes way up. Now, it affects it very strongly because we don't have that many points. Let's look at our own data now and decide if we want to delete points or not. How do you know whether, since R can be very strongly affected by these outliers, what do you do with them? So let's go to, let's look at our own data. We haven't done much of that yet. So let's look at survey 2 right here. And let's look at, here's the questions. And the one I'm going to look at is, let's look at this one. How many people have you been in a serious relationship with on our X, and how many people have you slept with in your life on the Y? And let's see if there's a correlation. So let's look at that. So we'll go to the scatter plot here, and we'll choose as X relationships. Where is it? Just relationships, and then we'll choose sex partners, how many as Y, and let's look at what we have. And let's look at the regression line. Okay, so there's our regression line, and we have a correlation of 0.33. Now, do we have any outliers? Do you see any outliers here? Yes, we do. Let me just look at this. Okay, it looks like this person is an outlier, observation 354, and observation 3, this is anonymous, so I don't know. And what it's saying is this person never had a relationship, or maybe this is one, no, I'm not sure, but had 50 sex partners, maybe more, but we cut it off at 50, and same with this one. Now, there's no one down here, there's no one who's had tons of relationships, and this person is the best here on this outlier. This person had 6 relationships and no sex partners. Well, that's all right. And these people are right on the line. So now the question is, what happens? I want you to know, I want you to think. It's a little bit harder with real data. What do you think will happen if I delete these people? Do you think this R is going to go up or down? Let's just do it and see. All right? So we're going to delete them and see what happens. I think it's going to go up because they're very far off the line here. Let's delete this one. Yes, it went up to 0.4. Okay? It didn't affect it as much because there's lots of points here. And there's a whole lot of points here. But the question is, should we delete this person? Do you think it was a typo? If it was a typo, or if you think they were lying or something, you would delete it. But we really don't have that information. What would we do? We'd have to look at all his other data, see if he's like making up crazy answers for everything, he or she. Or, you know, if it was height and weight and somebody put in that instead of 6 feet, they put, you know, 6 inches or something, like you know it's a typo. But here, you're not sure. So let's go back to the document camera. And so the question, what I was trying to answer here was outliers have a strong effect on the correlation coefficient, but they should only be thrown out for a good reason. Don't throw them out just because they're outliers and you want to make a nicer plot. Okay, only throw them out if you think they're lies or typos or something. But you should, probably report the correlation coefficient both ways, with and without the outlier, and just realize that if you don't have very many data points, they can really affect your correlation. Okay, so I think that's it. And let's move on to the next page. Okay, so here we are on something called ecological correlations. It's not a very intuitive name. What it refers to is correlations based on averages instead of on individuals. You're going to see this a huge amount in social science data. And it's not wrong, it's just it doesn't give you the same results as if you base it on individuals. Okay? So here's, for example, this is real data. The correlation for education and income for US men is about 0.44 overall, individual men, right? That's the individual. But if you take the average educational level and average income for each state and look at the correlation between the 51 pairs, you get 0.64. So here you have millions of points and you condense them into 51 points. And what that does is it reduces the within state scatter. Every state just has 1 point instead of all the scatter, and all you get is the between states scatter. So within each state there's a lot of spread, but taking the average wipes out that within state spread and just leaves the between state spread. So often it inflates R. Not always. I mean, you can have other things happen, but usually it inflates R. That means it makes it stronger negative or positive. Makes it closer to an absolute value to 1. So here's a very simplified version of this. It says the graph on the left represents income and education. It's just made up just to show you the point. For individuals in 3 states. Okay, so here you have the individual education, individual income for 3 states. So let's say here's 4 people in state 1, and then you take their average education and their average income and you get 1 point right there. Now let's do the same with 2. So now there's 1, 2, 3, 4 people in state 2 here, and here you condense them into 1 point. This is just just to give you the idea. And now let's do state 3, make these those. There's a lot of spread in state 3, but you're changing it to just 1 point. Now, do you see how this right here has a stronger, so R based on averages eliminates within group, within state, or within groups, within state scatter, and leaves only between state scatter. So you usually get a much stronger, so R is usually much stronger when you do this. So usually, not always, resulting in a stronger R, okay? Whereas here you can see you have a lot more scatter. So here, R based on individuals has more scatter because it has both the within group and the between group scatter. Okay, So that's the point. And a super simplified example is, let's say for each of 5 statistics classes, this is how people could lie with statistics. They could say, within each of the 5 statistic classes, the average percent on the midterm and the average percent on the final were calculated, and the correlation was 0.97. So they could say, oh, there's a perfect correlation between your midterms and your finals. No, that's based on averages. So this would be like, it could look like, okay, you have the midterm and the final. Think about if you only have 2. Well, then you're going to have a perfect correlation, whatever 2 points, right? But you have like something like that. But that doesn't mean, and people will apply that to individuals, where there's hundreds of people, and there's a lot more scatter, and that does not mean, so R here is 0.97. That's in the average one. But here, when you look, this is the midterm and the final, here it's going to be a lot less. So just beware of that. People love these strong correlations, and I've seen this happen over and over again in newspapers, and then these are not lies. They're just true of the aggregated data. They're not true of individuals. You cannot apply it to individuals, but people often make that crossover, so don't do that. Understand? Okay, now correlation is not causation. We've said this many times, and we're going to look at how we can tease causation out of correlation. But for now, I just want you to remember that this is just a reminder. We've talked about this a lot. And here's 2 examples of it. So let's move on. And our summary. And now, okay, so now we're going to look at how you actually calculate the slope of how you actually calculate the regression line. So let's look at it. First, let's look at we did a lot of this in answer to a question, but so this should be very easy now. So how can we use the correlation coefficient to estimate the average value for y value for given x? All right. Well, when r is equal to 0, if you go up 1 standard deviation from average in the x direction, then y will go up 1 standard deviation. We just looked at that. That's the SD line. And we looked at this too. If r increases 1 standard deviation, then y on the average either goes up or down, and you just get a random scatter plot. So this is the correlation of 0. Now we looked at 0.6. Here's 0.8. Here 0.6 is if x increases 1 standard deviation, then y increases only 0.8 standard deviations on the average. It's not exactly 0.8, it's just on the average. What do I mean by that? I mean that if you drew let's just look at our own data, it's more fun. All right, we're going to do this with our own data, so let's go to the PC. And do we have height and weight here? No, we don't have height and weight. We have it on a different survey. Why don't we just choose something else? How about, I know something that's strongly correlated is, let's see, we'll go to, we're going to look at this later, so we might as well look at it now. How much you party predicts a lot how much you drink per week among typical Stat 100 and 200 students. So here's this regression line, and there's a very strong correlation here between the 2 variables. So how do you get this regression line? Well, think about it. Think about this regressogram here, where, let me just see if I can. Okay, so for what is it? There's not a perfect line here. Like the SD, there's not a perfect correlation, right? So how are we getting this best fit line? It's called the least squares line, the best prediction of y from x. an intuitive way to think about it is, as it's the line that within each little vertical strip here, like vertical strip here, like these are the people who had 29 party hours, and there's only one, so it has the average here. This is the average of just one. Here's a better example. People right here in this vertical strip partied 20 hours per week. So there's a little horizontal line that indicates the average in that vertical strip. See, in every vertical strip, an average is computed. And that's what these little horizontal lines are. And what the regression line is the best fit through all those horizontal little lines. You can't hit them all, obviously, because if they formed a line, it would be a perfect correlation. But it minimizes the errors. Like if this line, for example, when you go, this is our best prediction, and that's the average. It didn't quite hit it, but this is the line through all these points that minimizes these errors up here, the sum of the squared errors. Think of it as the sum of the absolute value of the errors, right? So it's called the least squares line. And it's the regression line, as opposed to the standard deviation line, which is the line that of equal standard deviations in x and y. So for example, is anybody on this line? Yeah. Well, here they happen to be the same thing. Where they cross is the point of averages. But this person is exactly, they're not the same thing. This is the average. There are only two people in this strip. But this right here, person is exactly the same in z-scores in x and y. So that's the idea. Any questions on that? Or did that, raise your hand if that clarified things at all. Raise your hand if it didn't. Raise your hand if you didn't pay any attention. Let's do an eye clicker. I'm curious. Well, we don't have time. All right, back to the document, Kara. I think this stuff is really cool to get an intuitive explanation of this so often. Regression's really fun, looking at correlations. Everybody wants to know, like, what's related to what. I mean, that's how we think, and it's so much fun to, and our intuition about it's terrible. Let's just see. Here's an example where it might be terrible. Like you would think that, I haven't looked at this, but let's look just to make a little bit of an impact. All right, let's look at how much you drink in your grades, or your your GPA. Let's see if that, you'd think there'd be a negative correlation, because you're always told that, right? But maybe not. Let's see, how much you drink, maybe there is. Drinks and GPA. Let's see. Does how much you drink predict your GPA? Let's look. It does in this class. It has a negative correlation of negative 1.633. Sometimes it doesn't in certain classes, but it might not be as strong as what you think. Okay? Does it predict how many sex partners you have? Slightly, yeah. So here they're agreeing with your intuition. But check it out. It's really fun. Sometimes it's fun when it either agrees with your intuition or when it's so counterintuitive, and then you'll remember it better. So I strongly encourage you to look at our data. Meanwhile, we have to get back to the document camera before I lose your attention altogether, because we're about to do interesting stuff. All right, so we already covered this. The slope of the SD line is SDY over SDX, and the regression line is flatter than that, okay? It's flatter. This is by a factor of R, right? So this regression line is always less steep. That's what I just said, by a factor of R. And you should know this, the slope, I'm just going to say, know this, it will not be given to you, this equation. All right? Now, so this is what we just did in class. And this, on looking at our data program. All right? It's the same idea. Now let's move on and let us actually make some regression estimates. So we're going to do it two ways in the 20 minutes we have left. And this, we're going to do it by converting to z-scores. So we have these values here, and here's height and weight, actual data, and we're going to make predictions for people. So, for example, somebody who's 71 inches tall, right up here, how much do they weigh? That's what's asking right there. So let's think about what this says. So this is the regression line, and this is the SD line. Now, how are we going to, somebody who's 71 inches, you could go over here and try to read it, but it's hard. So instead, let's look at this. So what are we going to do? So the first step, it's a three-step process. We're going to convert to z-scores because, right? So that's our first step, convert to z-score. Then we're going to multiply by r, and then we're going to convert to get the z-score for the y variable, and then we're going to convert that z-score to a y value. So those are our three steps. And here's all you need to know are these 5 summary statistics, the averages for both x and y. Now, which one's x? We're predicting. Which one are we predicting? We're going to predict, which doesn't make sense to predict. I think it makes sense to predict the weight from the height. So that's going to be our x and y. And that's the graph. And now here's the averages, standard deviations, and the correlation coefficient. So we're going to use all this. So we're going to take a height, that's 71 inches right here, and we're going to get our best prediction for the weight. So first you convert to a z-score. So we'll get zx, z for the x. And how do we do that? Well, you just take the value, 71 inches, minus the average right up here, which is 65 inches. We're all in inches here, divided by the standard deviation. And that's a z-score of 2. Now, if there was a perfect correlation, here, let's just put, we're going to get cy, and then we'll get the value. If there was a perfect correlation, we'd say, okay, his weight's 2. And then, as a z-score, and then he'd be 2 standard deviations above average in weight. He'd be 135 plus 50, 185. But he's not, because he's not our best prediction. We're looking at this right here, this little vertical strip here, 71. These are the people who are 71 inches tall. We're looking at that. And yeah, he'd be up here at 185. There are people up there who are the same in height and weight, but there's a spread, and our best prediction is right here. That's what we're trying to get. That's much lower. And what's it lower by? It's lower by, you multiply the z-score by the correlation coefficient times r, and that's what makes it lower. So you're going to multiply it by 0.5, and then our best prediction is only 1 standard deviation above average. So instead of, here's the average, and plus 1 standard deviation above average. So that's 160. So that's what we did here. So let's just show that. So here we have the person who's 71 inches here, and the regression estimate right here, this point, is 71 inches, but 160 pounds. That's what we did here. So if you went across here, instead of the SD line, which would be, right? So to bring back what the picture we drew before, the relationship is this. If we went over, I'll just draw it over here, a certain amount of standard deviations in the x direction, this is 0, that's 1, and this is 0.1, 2, 3, 4, 5. That's where that 5 is coming in. That's r equals 0.5, 0.6, 0.7, 0.8, 0.9, etc. It's flatter, it's less steep. So that's the idea. Understand that?
Like this one's 0.05.
Oh, it's not 0.05. Good catch. Thank you. Nice catch. All right. So You know it couldn't be that. That would be like no relation almost. All right, let's do the next one. Okay, so what about if somebody is 65? That's a z-score of 0. They're right at the average. You multiply by r. It's just going to give you a z-score of 0. So a z-score of 0 in weight is just the average. All right, and that's the point of averages right here. And the point of averages is always, this is the point of averages, and it's always point of averages. And it's 65, 135, or 0, 0 is the z-score. 65 inches, 135 pounds, or a z-score 0, 0. And that's on both lines. All right? Now, it's where the two lines crossed. And now let's look at this one. It's a negative correlation. So we have, and not a negative correlation. The person is below average, excuse me. So this person is below average by 3 inches when we divide by 3 inches. So he's 1 standard deviation below average, but as you have to multiply, our best prediction is negative a half a standard deviation below average here. And that would be what? You start at the average and you want to go down plus negative 0.5 times the standard deviation, which is 25 pounds. So that would take us down to minus 12.5, 122.5. Okay? Does people understand this 3-step process? Very intuitive, and it helps you understand what regression is. Now we can do the same exact thing by the regression equation. All right? We can get an equation for this line. And that's what we're going to do now, get an equation. Instead of do it in, sometimes it's easy to do this way in your head, but if you have a lot of predictions you want to make, you want to get the equation for that line. Yes?
How on the right, like where you have the line equals 0 and then you have the perpendicular line going up,
Yeah.
what are like the dashes going up and how many and where do you
Okay, good question. So where she says, what are we doing here? What do these dashes represent? I'm saying this right here is should be the average weight, right? Right across the average here. That's what I'm doing. That's the average weight. Now, 135. Oh, that's a correlation of 0. We know, right? You understand that? And that's 1. So all we're doing with this is they're like percentages. We're saying the regression line, how far up is the regression line, the slope of the regression line? I'm just comparing, like this is really steep. If this is 100%, then what percent steepness is it compared to that? So I'm just going from 0% to 100% or 0 to 1. So I marked it off as decimals, 0.1, 0.2, 0.3, and I'm estimating. But where it hits this is exactly R. Does that make sense? If R was 0.9, we would have a regression line that was 90% of the way up. Does that help? If R was 0.1, we'd have a very flat regression line that was only 10% of the way up. Okay. Does that make sense to you now, everybody? All right, good question. And let's move on. So now we're just going to get the slope of the regression line. Okay, so get the whole equation. Now here is the equation for a line. This is the intercept, and this is the slope. I wrote it this way because we're going to be adding more predictors. So the intercept is called B0. The first x variable will be called the slope of it, B1, B2. We're going to go into multiple regression. So this is the way it's written in statistics. It's the same as y equals mx plus b. And this little hat just meant I was making a prediction here if I was doing inference. Okay, so don't worry about that. But this is the intercept here, and this is the slope, and it's the same thing. We just write them both as b's. Okay, our second variable is going to be b2, etc. So now we know already, I said that's what you need to memorize. That's the slope of the regression line. So moving on to our own data that I just showed you, 364 Stat 200 students answered that question, and I rounded the statistics. You can look on it and see. But here was the average number of party hours that you guys answered this semester was 3.6, 4.1 for drinks, 4.8, 3.6 with a standard deviation of 4.8, 4.1 with a standard deviation of 7.7. All right, now R we saw was about 0.6, it was 0.58. That's the real data I got. Now, how do we find the regression equation from that? So what I want to find is, first of all, which one's Y and which one's X? Y is always what you're predicting. So we are predicting drinks from party. I'm not always going to, you won't always find X on top. Y is always what you're predicting. Okay? So now, the first thing we're going to do, so we want to get this equation. Y, how many equals something, the times X. Whoops, I don't want to write it that way. I'm going to write it this way. Y equals some intercept plus some slope times X. So I want to fill in those two blanks. All right, I want to get those two things. So find the regression. So first we'll find the slope. First step is find the slope. And this is super easy. It's going to be equal to what? R times SDY over SDX. R is given to you, 0.58. Now, which is X and which is Y? Okay, you want Y over X, rise over run, of course. Rise over run, we're going to be getting, so that is, here's our SDs. So don't make it, so you know it's either 4.8 over 7.7 or 7.7 over 4.8, but you want Y over X. So it's 7.7 over 4.8 drinks per hour. Okay? And so how do we get that? We'll just do it. So that's equal to, what did I do there? Oh yeah, I didn't do it out yet. Okay, so this comes out to be 0.93. That's what we're going to put in there. So you can think of it as, oh, people on the average drink one extra drink or 0.93 extra drinks for each extra hour of partying. That sounds about right. If you go out partying, about 1 drink an hour, I don't know. Something like that. Okay, that's what that means. Now, does everybody understand that? Questions on that? All right, now how do we get the intercept? Well, the intercept, so we're just trying to solve for this. Well, we can plug any Y and X in here, any point on the line, and we'll get that. But the only point we know is the point of averages, right? So why don't we plug in for X, 3.6. We're going to plug in for X, the point of averages. So we'll plug in 3.6 there. And we're going to plug in for Y, the point of averages. So we're going to plug in 4.1. And then we'll solve for the intercept. That's all we'll do. Okay? So to find intercept by plugging in point of averages. All right, so let's do that. So we'll just plug in a 4.1 right here for Y, and we're saying that equals the intercept, which we're calling beta 0, plus 0.93, and we're plugging in 8. What does it even say? 3.6, the point of averages, right? Times 3.6. And then we'll just solve for the intercept. So I did that, and I got beta naught equals 0.75. So that is right here, 0.75. All right? So that's our regression equation. Sorry, it looks so messy. I'll just say Y equals, this is it right here. That's what we're going to be using. Okay. And so now it says use it to make an estimate. Now that we've got it, we can just plug in for X and solve for Y. So plug 20. So we're going to make an estimate for somebody who parties 20 hours per week. And I did that, and I got 18.675. I'm kind of crazy to make it so accurate, but that is how many drinks. Okay? And now, how do you interpret the slope and y-intercept in the above equation? Well, the slope, we just said, is what? The slope is, on average, it means that people drink what? On average, 0.93 drinks per hour. So for each extra hour, the number of drinks increases on average by 0.93. That's the slope. When you go up on the, for each extra drink, on the average, there's a big scatter. That's how many we estimate people drink more. All right, and what's the intercept? The intercept, the y-intercept, is when x is 0, what's your y? So it means on average, people, when x is 0, people who party 0 drink 0.75 drinks, have That's what it means. It's not, how much they consumed. So we can, if you look at the graph, you can see that that looks about right. And this is if you look at our data, I rounded everything, but you'll get something very similar. And let's see if there's anything. That's it. We finished these chapters. And we're good. And so the homework is posted, and explore the data set. It's kind of interesting. Your survey data.